All right, let's get started. Welcome, everybody. So I'm pleased to welcome our speaker today. It's Matt Brin from Binghamton University, and he's going to tell us something about ordinals and subgroups of Thompson's group F. Please.
Okay, thank you. Thank you for the opportunity to speak. As this notes, this is joint work with Colin Blake and Justin Moore. And the purpose of the talk is to describe a family of groups and to describe the structure of the family. There'll be much less description of the structure of the groups, but you'll see the structure of the family resembles the structure of an initial interval in the ordinals, and that's why the ordinals are part of the title. All of the groups in the family will be subgroups of Thompson's group F, which is why subgroups of Thompson's group F is in the title. But that's the end of that. That's literally the only role that Thompson's group F has in all of this. And other than mentioning that again, that's not going to get mentioned. The dominant feature of all of this are the ordinals, and the initial interval that we'll be dealing with, I want to explain. So this slide is just to get in the right mood. And when people list ordinals, they get tired and say things like ... which means that they're skipping an interval. Here, you're skipping an interval with the order type of the natural numbers. Doing that again, you get first to little omega, the first infinite ordinal, then omega times 2. The same kind of skip gives you to omega times 3. If you get tired of that, you skip an infinite number of skips, you get to omega squared. Then the skipping starts to escalate, and going from omega squared to omega cubed and omega cubed to omega fourth are increasing complexities of skipping. You get to omega to the omega. Then you start piling the omegas on top of each other. And finally, you get to epsilon naught, which is the limit of omega to the omega to the omega to the omega ... And it's the smallest ordinal solution of little omega to the alpha equals alpha. And that's as far as we're going to go. That's as far as the slide goes. It's as far as the entire talk goes. And we'll leave it at that. The other aspect that this family of subgroups reflects is not only the order type, but also some of the arithmetic. And this slide is just to review some of the oddities of the arithmetic of the ordinals. One way to define addition is to simply concatenate ordinals. And if you take a single object and you put it in front of something with ordinal type little omega, so if you take one object and put it in front of the natural numbers, it still has the order type of the natural numbers. So 1 plus omega equals omega is a legitimate thing to say. But if you take a single object and you put it after the natural numbers, you get a very different order type. So addition of ordinals is not only non-commutative, it's not cancelative. Similarly, multiplication, if you define multiplication by the cross product and you make the second coordinate more important, then 2 times omega is omega copies of 2. And if you take 2 elements and 2 more and 2 more and string them out, you just end up with the order type of the natural numbers. On the other hand, if you say omega times 2 is to be 2 copies of omega, then you have a copy of the naturals followed by another copy of the naturals. You have infinitely many elements with infinitely many predecessors, and it's a very different result. If you do something like take omega plus 1 and multiply it by omega, you string out all the omega plus 1s. Each one gets absorbed by the following omega, and you just end up with omega squared. Similarly, omega plus omega times omega gives you the same result. Do that in the other order, and it's quite different. Okay, what does this have to do with groups? The Wreath product is going to show up, and I'm very reluctant to define it. this slide is self-contained, and when it becomes less self-contained, we'll see what people are willing to live with. So if I look at z plus z, the first z I want generated by A, the second z I want generated by T. This is by definition a countable number of copies of the left-hand z indexed over the integers. That direct sum is the normal subgroup in a semi-direct product, where the top group is the right-hand z, and the action of the generator of the top group is to simply shift the index. So conjugation by T takes the copy at 0 and it conjugates it to the copy at 1, and so forth. If I look at the Wreath product of z plus z on the bottom with z on the top, the generators on the bottom being B and C, generator at the top I'm calling S. You take a countable collection of the bottom group and you index it by z. The generator of the top group also shifts it by 1. But this is exactly the same as taking a countable direct sum of copies of z indexed over the integers. And now the top group, the generator, will shift by 2. And so A and B are quite different. However, A embeds in B. You take the bottom z over here, you embed it in the left of the bottom 2 z's over here. You take the top generator, you send it to the top generator here, and you have embedded A into B by skipping every other bottom z, and you have embedded as an infinite index subgroup. On the other hand, B embeds in A by sending the left z to the original bottom z, sending the right z to a conjugate of the bottom z, and then you send the generator at the top to the square of the generator here, and that embeds B and A as an index 2 subgroup. So in spite of the fact that A and B are not isomorphic, they're bi-embeddable, and this reveals that we're going to be interested in the bi-embeddability classes of our groups rather than the isomorphism classes. And this is supposed to remind you of something in the previous slide where extra information gets absorbed under the right kinds of operations. And if you want something to do, you can take as exercises that not everything is bi-embeddable with everything else, that they actually are going to be some differences. Anyway, giving this kind of talk is kind of like talking into an empty barn. Shout out if I'm going too fast or I'm saying anything unclear. Okay. With bi-embeddability classes, we're going to need something that varies with bi-embeddability classes and is invariant in each one. And in this particular instance, the elementary amenability class is going to be important. First of all of the groups are going to be elementary amenable, which might be of interest. And second of all, the analysis, whatever there is, will be making heavy use of the EA classes. So let me just go through this. It's probably familiar to a lot of people. So the elementary amenable groups are in a class called EG. The group is filtered, and EG0 at the start is all finite groups thrown together with all abelian groups. And to get a group in a new class, you can do it either of two ways. You can either do an extension with a normal subgroup and a quotient coming from the class before, or you can do a directed union where all of the subgroups come from classes that have come before. And hopefully this makes clear that the groups in one class all appear in groups of the next class, because you can always extend by the trivial group, or you can always use as one of your subgroups the group itself. So EG0 is contained in EG1, which is contained in EG2, ... At a limit ordinal, you simply take the union of all of the previous classes. One of the consequences of that is you never introduce any new groups at a limit ordinal, which will be mentioned about 5 lines below. And then the elementary amenable groups are simply, or the class of elementary amenable groups is simply the union of all of these classes that you have built. If you have an elementary amenable group, then it's elementary amenability class. I will never repeat that phrase. The EA class is the first class where it shows up. It's the least ordinal where the group shows up in EG alpha. EG, EA of G is never a limit ordinal because no new group is ever introduced when you have a limit ordinal as the subscript. Also, if you have a finitely generated group, you cannot get a finitely generated group for the first time by method 2, because eventually the finitely many generators have to be absorbed. So you will never get a new group that way, which means you can only get a finitely generated group for the first time using extensions. The normal subgroup and the quotient cannot come from a class with a limit ordinal. So they have to be at least a limit ordinal plus 1. So your finitely generated group has to have class at least a limit ordinal plus 2, which is not terribly important, but it explains 2s that will appear in some of the future slides. Anyway, the EA class is a bi-embeddability invariant. If you have a group embedding in another group, if the larger group is elementary amenable, so will the smaller group, and its EA class will be no bigger. So things in the same bi-embeddability class have the same EA class. Okay. Wreath products will come into use a certain amount, and skipping exactly what Wreath product I'm using, Wreath products tend to raise the EA class. So if you have an infinite finitely generated group that's elementary amenable, then, and it's EA, no, it even works with 0, even if the EA class is 0, then the Wreath product of that group with itself will have raised the EA class by either 1 or 2. In the special case where the infinite direct sum of copies of that group does not raise the EA class, then in fact it raises the EA class. The Wreath product raises the EA class by exactly 1. And the new group that you have has exactly the same property. The infinite direct sum of copies of that does not raise the EA class of the group itself. So anyway, Olshansky and Osin used facts like this to construct for every non-limit countable ordinal a countable group with that EA class. And if that non-limit ordinal was in fact at least some ordinal plus 2, then the group they constructed is finitely generated. And we do considerably less. As I said from the first slide, epsilon naught will be the cap of everything that we do. And we will see that in a minute. So here is the first look of what we do. So every ordinal on this page is no more than epsilon naught. And for each such alpha, we create a finitely generated group, which is elementary amenable. This alpha is not the EA class. It's just our indexing. We start slow. We start with the trivial group. Going up by 1 is to simply take a direct sum with the integers. The ordinals index the bi-embeddability classes. So these things go strictly up by bi-embeddability. They do not go strictly up by EA class, but they do go up. And if the index has this very special form, then we can tell you exactly what the EA class is. If the alpha is not 0, it has this form. If the alpha is 0, then this is omega to the 0, which is 1. This is just omega to the 2n, and the EA class is just n plus 1. The formula is not too critical. It will show up a little later. There is a way of taking the bi-embeddability classes that we create and mapping them up so that they are separated by the EA class, and that will turn out to be important. 7 is the big deal. These are pretty, and I will show you exactly how pretty shortly. And in fact, they're fairly easy to construct. The construction is not the problem. It's the analysis that's the problem. And if you hand me an ordinal in Cantor normal form, which will be explained in the next slide, then there's a procedure that can be followed to actually write down the group, not in terms of generators and relations, but in terms of very specific homeomorphisms acting on the unit interval, which is why they end up being subgroups of Thompson's group F, which is the one and only time during the talk that I will mention Thompson's group F. Okay, what's the Cantor normal form? If you have an ordinal, then there's a unique expression of that ordinal as a polynomial in powers of little omega, where the exponents are a non-increasing sequence of ordinals. However, if alpha is greater than epsilon naught, you're not really simplifying anything. Epsilon naught equals omega to the epsilon naught is, in fact, the Cantor normal form for epsilon naught. However, for all ordinals less than epsilon naught, then in fact, the highest exponent will be less than your ordinal and also less than epsilon naught, therefore. And so it has an expression in Cantor normal form with smaller exponents, and all of those exponents will have Cantor normal forms with even smaller exponents. And since everything is decreasing and the ordinals are well ordered, this actually stops. And so every ordinal less than epsilon naught has sort of a finite repeated polynomial expression, which is kind of tree-like, with the operations of addition and exponentiation base little omega. And just for illustration, I took a nice simple expression here and made it worse. I'm not sure why I did that. Anyway, because weird things happen at the bottom of sequences, the notion of EXP will change a little bit, but we'll wait for that to happen. So what's strange about our results is the ease with which they can be played with. And usually when you build something recursively, you go through a certain process. You start with some base object. You explain how to take any object and build the next one. If you reach a limit ordinal, you explain how to build the one at that limit ordinal based on whatever you built before, and so forth and so on. And this is sort of the outline of the Olshansky-Osin construction. However, we're different. And if you give me a couple of these things with the one on the right less than the one on the left, I can build the group that corresponds to the sum very easily. I can build the group in some sense that corresponds to the product, but certainly that corresponds to alpha times omega. In fact, I can even build the group corresponding to little omega to the alpha all as easily as just building g of alpha plus 1. And in the previous slide, I said g of alpha plus 1 is just g alpha plus the integers. And so that's actually a fairly strong claim. Also, there's a nice subsequence. The groups corresponding to just a tower of exponents of little omega are all two-generator groups. And strangely, going up by two exponentiations base little omega is actually easier than going up one, which is kind of cute. A certain asymmetry in some definitions gets ironed out if you do two of them rather than one of them. So as it says, it's time for pictures, and here are some pictures. So I said all of these groups are groups of homeomorphisms of the unit interval. Here we have two homeomorphisms. This one is called F4 because you see 4 wiggles. This one is called F3 because you see 3. Here you see the two of them together, and this happens to be the group corresponding to G sub omega to the omega to the omega to the omega. And it has EA class omega to the omega, and there's the promised +2. The next slide is going to discuss the anatomy a little bit, and I may as well talk a little bit while these pictures are up. Here is a component of the support of F4. In it, points in the interval are being moved to the right. Because it looks like a bump, we will call this a bump. Because points are moving to the right, we'll call it a positive bump. Here's another positive bump. Here is a negative bump because points are moving to the left. Here is another negative bump. And so F4 has 2 positive bumps and 2 negative bumps. F3 has 2 positive bumps and 1 negative bump. And when they come together, the F4 looks more important. That will be made formal in a minute. And each bump of F4 has both fixed points and non-fixed points of F3. And I'll therefore declare that this bump is active because of that. This bump also has fixed points and non-fixed points of F3. So does the third bump. So does the fourth bump. And so F4 has 4 active bumps. And that fact will be repeated in a minute. So the next few slides are to discuss reducing everything that I'm talking about to collections of numbers. And this slide discusses where the first number comes from. Before I get into it, let me explain the pictures on the bottom. The pictures on the bottom are like the pictures on the previous slide, except they've become lazy. And the whole picture has been tilted 45 degrees, and the horizontal line is now the line y equals x. And we're not bothering to draw the x and y axes, which are at 45-degree angles. And so A is a function here with 3 bumps, B is a function with 2 bumps, and I'll get to that in a minute. So this just repeats what I said before. A component of a support is a bump. There are positive bumps that move points to the right, negative bumps that move points to the left. F4 is 2 positive, 2 negative. F3 has 3 positive, 2 positive, 1 negative. And the oscillation number of these two functions is 4 because of the explanation that I gave in the previous slide. And this is not symmetric. F3 is to the left and F4 is to the right because F4 is the more important function. And why is it more important? Because the supremum of its support is greater than the supremum of the support of F3. And that will be used to order these things. So a pair of functions is standard if it satisfies this recursive definition. It has oscillation n plus 1 if you modify the pair of functions by taking the larger function and simply erasing its rightmost bump and its leftmost bump. And if you do that, then what's left is supposed to become the smaller function. And that new smaller function with the unchanged previous smaller function is now supposed to be a pair with oscillation number n. And when you finally get to oscillation number 0, then the supports are going to be disjoint. And the more important function is supposed to have the supremum of support to the right of the less important function. And that's what we're showing here. So if you go through the sequence, A is the dominant function, B is a lesser function. The oscillation number is 3 because every bump of A contains both fixed points and non-fixed points of B. When you remove the leftmost and rightmost bump of A, then you have this pair where B is now dominant and the oscillation number is 2. Now you're supposed to remove the leftmost and rightmost bump of B, which leaves nothing, which we don't like. And so the rule is at the left end of the positive bump, you put a tiny little bump and leave it there. You now have a pair with oscillation number 1. Now we're supposed to remove the extreme bumps of A0. Again, following the rule of not wanting it to vanish, you put a little bump where the left end was, and you have this pair, which has oscillation number 0. All right. We now understand pairs and their oscillation numbers. Now, if I have a finite collection of these things, we call this collection standard or good or whatever, if every pair is standard. And I can then write out the oscillation numbers of all of the pairs in an upper triangular matrix. I was having fun playing with colors here. It's a strictly upper triangular matrix. We don't care about the relationship of a function with itself. And you end up with a bunch of numbers. And the nice thing about these numbers is that under some restrictions that I will get to in a much later slide, certain things happen. I didn't draw these pictures very carefully. They don't look like elements of F. Elements of F is supposed to be piecewise linear because it doesn't matter. There's a certain stability here. You can change the picture very, very slightly and still have the same isomorphism type. So if I replace those pictures by ones that are piecewise linear, but decently close to the original, I still have the same group, which is how these things end up in Thompson's group F. The isomorphism type is completely determined by the collection of numbers. We call the triangle of numbers the signature. That turns out to be a very big deal. And we'll explain that shortly. If somebody hands me a upper triangular matrix of non-negative integers and claims that it's the signature of some group, I can tell if they're lying by a very simple test that will be explained later. And all of these groups, all of the groups that you get by these pairwise standard collections are bi-embeddable with our G alphas. They're not necessarily all of them G alphas. Every G alpha is one of these pictures. Not every one of these pictures is a G alpha, and I can explain it now or later. I'm sort of tempted to explain it now. The Cantor normal form is a restrictive way of writing down a polynomial. You can write down a perfectly good polynomial that's not in Cantor normal form, but it's a perfectly good ordinal. So 1 plus omega is not in Cantor normal form, but it's also a decent ordinal. Corresponding to that polynomial, I can write down a group, and it won't necessarily be one of the G alphas, but it will be bi-embeddable with one. And so in order to make sure that you have a G alpha, you're going to have an order restriction that sort of follows the order restriction in the Cantor normal form. And it's time for another picture. So here we have 4 functions. I'll explain how this picture was made in a couple of slides. And on the right, we have the oscillation numbers. I'm not going to go through all 6 of them. A and B. B has 3 bumps. Each bump of B has a fixed point of A and a non-fixed point of A, and that gives the oscillation number 3. However, the relationship, say, between B and D is much simpler. all of this waviness of B doesn't really matter. It has fixed points and non-fixed points in this bump of D, but it's still just 1 for D. And so the oscillation number of D and B is only 2, even though B is bouncing around quite a bit. It's a standard collection. The signature is shown over here. It happens to correspond to the group G sub omega to the omega plus 2. The EA class of this is this polynomial. And in order to explain how this thing arose in our system, we have to start doing some arithmetic that mimics the arithmetic of the ordinals. As I said, because weird things happen at the bottom, we are redefining EXP. It's omega to the alpha for an infinite alpha. It's omega to the alpha plus 1. Sorry, try again. Omega to the alpha minus 1 for a finite alpha. And EXP of 0 is 0. And based on this and operations in the next slide, we'll start imitating some of the operations on the ordinals. Now, the previous slide claimed that the isomorphism type of these groups is completely determined by the signature. So I can talk about the group generated by a set of generators, or I can talk about a group specified by a signature. And I'll do both in the next slide. So here's a bit of arithmetic. And one second here. Just want to see something. All right. So let P and Q be signatures. And they're upper triangular matrices. And if I want to write down what I think of as P plus Q, I will take Q and I'll put it in an upper block. I will take P and put it in a lower block. I don't care what's in the lower left part. And in the upper left part, I will simply fill all of the entries with a 0. Now, if you fill all of the entries with 0, then the interaction of all of the generators specified by Q and all of the generators specified by P will have disjoint supports. Also, the ones in Q will be above the ones in P, and so they're off to the right. And so basically, I'm getting the group specified by Q to the right of the group specified by P acting on the unit interval, and I'm just getting the direct sum. And so here I get the claim that the group specified by the sum of the signatures is in fact the sum of the two groups specified by the two signatures. I can also define this operation where I do the same thing, except now the upper right rectangle is filled entirely with ones, and I will claim without justification that corresponds to the kind of Wreath product that I am talking about but not defining. At this point, group operations vanish and are replaced by magic. It turns out that if you have a signature corresponding to some collection of these functions, and you simply add 1 to every oscillation number in that signature, you get a new signature. And when you do that, you get a brand new group. And the question then is, group theoretically, what does it have to do with the group that you started with? And we have no answer to that. It's just a new group. So the arithmetic, we won't start with 0. 0 corresponds to the trivial group. It's hard to make any progress with the trivial group. If you take the direct sum with the trivial group, nothing changes. If you take a Wreath product with a trivial group, nothing changes. So we will start with a group generated by one element, which is Z. Unfortunately, the oscillation matrix has no interesting information in it. It's a 1-by-1 matrix with data that we don't care about. Still, we can refer to it. And if I have an oscillation matrix corresponding to some G alpha, and if I have an oscillation matrix corresponding to some G beta, with beta the smaller, then you add the signatures together using this method. I claim that you have the sum of the groups that corresponds to the group corresponding to the sum of the indices. Modulo some problems that you avoid by making sure that everything is infinite. The Wreath product corresponds to the group that corresponds to the product of the indices. And when you exponentiate the signature, you raise everything by 1. You get the group that corresponds to the exponentiation of alpha using the formula on the previous page, where you take the finite ordinals of special cases. And here are some special examples. The 1 by 1 matrix corresponds to Z, which is Z1, G1. 1 plus 1 is Z plus Z, that's G2. The exponentiation of 1 plus 1, I can actually leave this out. It's not necessary. It's this matrix. It is Z Wreath G, that's G sub little omega. And so using the exp formula addition, any G alpha can be created from basically Z by expressing alpha in Cantor normal form. And then there's my little reminder to point out that if you don't use Cantor normal form, you will get a perfectly good group that's not one of these G alphas. However, better than doing exp once is to do it twice. And the next slide starts explaining that. To do it twice, you add 2 to every single entry in the signature, which is all very well and good. But as far as pictures go, there's a very easy way to do this. You look at all of your generators in order, where the order is determined by the soups of their supports. So here A is the least element, B is the next, C is the next, and D is the largest element. This particular collection has oscillation matrix that looks like this. D and C have no oscillation with respect to the others. A and B together have oscillation number 1. And I want to exp squared this picture. And the rule is you start with the smallest, you go from least to largest. And what you do is you take each function and you put a positive bump to its right, extending all the way to the right. That's wrong. Son of a gun. That word is supposed to be negative. Everybody scratch that out and replace it by the word negative. I don't know how many times I've read this. Okay, and so let's do that. So we start with A, and we will put a positive bump to the right. We put a negative bump to the left. The picture turns into this picture, and all of the oscillations involving A have gone up by 1. The next one to be operated on is B. You put a positive bump to the right, a negative bump to the left. Everything involving B has gone up by 1. That column and that row have been increased. Do the same with C. That column, that row have been increased, and you do the same with D. And you get the oscillation matrix that was from 2 pages back. The picture is a little different. There's a tiny little bump here and a tiny little bump here and a tiny little bump here that make absolutely no difference to the isomorphism type. They don't change the oscillation numbers. And so even though this picture is technically different from this picture, it represents the same group. And here it is expressed in terms of the operation E, which is x squared star and plus. And so if you wonder, where did I get the picture on page 13? I got it this way. I started with something simple and just started making it more complicated. which is pretty much how you can do any of these things. You start with something in Cantor normal form, create an expression like this that expresses the Cantor normal form, and then work out how to draw these pictures. When things get complicated, it's not fun, but in theory, it's always doable. All right. Now what? So there's been a lot of numbers and not a whole lot of group theory. And so this explains a little bit of how some group theory comes into this. So we have a set of generators, and the largest generator we'll call T for top. All the other generators will be called the lower generators. I'll refer to that set by A minus. And it turns out that if you take all of the lower generators and conjugate them by the top element, then the group that they generate is not the whole group. And in fact, the whole group is a semi-direct product of that normal subgroup given by all of the conjugates of the lower generators conjugated by powers of the top generator, semi-direct product T. And so going from the whole group to what we've always referred to as the big normal subgroup is progress in simplifying. Somehow we've gone from a larger group to a subgroup, and if we can say something nice about the normal subgroup, like it's elementary amenable, then the whole group will be elementary amenable. However, this is not finitely generated and has infinitely many generators. If you take finitely generated approximations by, say, conjugating over some range, you still have an enormous group with perhaps an enormous number of generators. And this is supposed to be considered progress, which it turns out it is. And so going from the full group to some finitely generated approximation of this big normal subgroup we call a stripping. And it is provable that this is well-founded. And the eventual consequence is that all of these groups are elementary amenable. And that's kind of a big deal. That took us a very long time to work out. The strange thing is that in theory, there doesn't have to be any group theory. The signature is a numerical construct. It's a upper triangular matrix of non-negative integers. The stripping operation can be calculated purely numerically. In a couple of pages, I'll toss some formulas up and I'll just say, see, that doesn't look that complicated. And so you can actually do stripping without involving any groups. And the claim is that the stripping operation on a purely numerical basis is well-founded. And we don't know how to prove that. It's not like we tried very hard. The only proof that we know uses the group theory, and it uses the fact that the EA classes distinguish between some of the classes. Now, if you go back to the formula for the EA class, if I take a group G alpha and I replace it by G omega to the alpha, then I'm sort of embedding all of our bi-embeddability classes. I'm injecting them into the set of classes, but I'm injecting them in such a way that they are now distinguished by the EA class. And that's part of the argument. We can use some of the theory of elementary amenability classes to have some sort of control over what's going on. The other thing that goes on is to cheat. And one of the things about ordinals is that extra information can often be dispensed with without changing the ordinal. So for example, 1 plus omega is the same as omega, and omega plus omega quantity times omega is the same as omega squared, and so forth and so on. And so what we discovered is that you do a strip and you take off the top generator and you end up with this big normal subgroup, and you look at a finitely generated approximation to it. And you have a tremendous amount of information, a lot of which turns out to be unnecessary. And if you throw out those unnecessary generators, you have now cheated because you changed the group. But what turns out is you have changed the group, but you have not changed the bi-embeddability class. And so even though the group has gotten simpler, you have not jumped down an illegal amount. And that turns out to be key to the analysis. And that's as much detail as I can possibly give about that. Okay, I omitted some hypotheses, and I kind of like to explain them because I like them. I said that the pictures are stable. You can change a picture by a very, very small amount, and you're not changing the isomorphism type of the group in question. And to discuss that, we look at a bump. One second here. And a bump, the particular one I drew here, is positive. It moves points to the right. You take a particular point t, you look at its image f of t, if this is the function f. And between t and f of t, if you take, say, the half open interval that's closed at t, you have a fundamental domain of the action of this bump on its support. And the region to the left is a union of countably many translates of this fundamental domain. The region to the right is a union of countably many translates of this fundamental domain. And we call the region to the left foot. We call the region to the right foot. And it's kind of like a dance. If you have a whole bunch of these functions and their feet are not stepping upon each other, then the picture is stable. Slight changes to the picture do not change the isomorphism type of the group that is generated. And this turns out to be crucial to a lot of things. The fact that the stripping operation stays within the class of groups that we want to talk about is kind of cute. The stripping operation takes conjugates. And here, if you have a whole bunch of feet of other functions in this fundamental domain, which is where they have to be if they're going to intersect the support at all, because they're not supposed to be touching the feet of this function, then when you conjugate, those feet will get translated into copies of this fundamental domain in either the right foot or the left foot, which means they're not stepping on each other, but of course they're stepping on the feet of this particular function. But in the stripping operation, you throw away the top element, and that solves that problem. The feet are still disjoint. Anyway, the fact that these are stable under these slight moves is a result of the three of us with Kasabov and Zaremsky. And we called the condition fast because basically it means that these bumps are moving points fast enough not to interfere. I said there were some requirements for being standard, and it's pretty much what the pictures were showing. A standard function has to have all of its positive bumps to the right, all of its negative bumps to the left. If there's an even number of bumps, then half of them have to be positive, half of them have to be negative. If there's an odd number, then there'll be one more positive bump than negative. And the reason for all of that is the following. It is incredibly easy for a group of functions to contain a copy of Thompson's group F. And once that happens, it's not elementary amenable. And so all of these restrictions on the construction of our examples was a frantic effort to avoid generating something that contained a copy of F. And going back, I forget where, to this picture, This group is Z plus Z, obviously very well understood. That's Z Wreath Z, that's fairly well understood. That group has been pretty well understood since about 2005 and is known to be elementary amenable. This group was sort of nominated as a group to look at because it might not be elementary amenable. And after a couple of weeks of calculation, we figured out that it was, and that was the start of all of this. So when is a signature a signature? Okay, this slide is not to be absorbed. The point of the slide is it's a very simple numerical criterion on triples in your collection that will determine whether or not you have written down an upper triangular matrix that is actually the signature of a set of functions that are standard. How do you calculate the stripping? And again, the details of the slide, there's really too much information here. The bottom line is if you have a signature, a matrix of oscillation numbers, you want to look at the signature of a finitely generated approximation to the big normal subgroup. The calculation of that new matrix is extremely easy. The most important symbol in the whole thing, of course, is that minus sign. Numbers are decreasing. By and large, when you have a bunch of numbers and something decreases, you might suspect that it's well-founded, that this operation is well-founded. And so there was every indication that this thing was well-founded. The proof of that was a mess. And as I said, the construction of these groups is very easy. The analysis of these groups is quite something else. Anyway, what we don't know a lot. We have a set of very, very, very specific examples that get quite complicated. And that's pretty much it. If you start violating any of the restrictions on the previous pages, we have no idea what goes on. Initially, this was to understand subgroups of F. Up to isomorphism seems to be a bit much. Up to biembeddability seems a little more practical. F is a subgroup of the piecewise linear orientation preserving homeomorphisms of the interval. Many of the properties of F are already expressed in the group PL plus I. And so you can ask the same question of PL plus I, try to understand the subgroups either up to isomorphism or up to biembeddability. And all of the examples we know about fall into either of two categories. Either a subgroup of PL plus I that we know about contains a copy of F, or it's actually a subgroup of F. Not only that, if it does not contain a copy of F, not only is it isomorphic to a subgroup of F, it's elementary amenable, and the conjecture is it's isomorphic to a subgroup of one of these G alphas. And so it would be very interesting to find a subgroup of PL plus I that does not contain a subgroup of F, but is not elementary amenable. I kind of believe that no such thing exists. Anyway, some oddities. The biembeddability classes of F, even though we believe that they're all elementary amenable, they actually don't form a chain. And there are elementary amenable subgroups of F that are not biembeddable with any of the G alphas. They do embed in some G alpha, but they don't biembed with it. And for groups that are bigger than F, there's not a whole lot known about that, but there is an infinite ascending chain of groups that are not biembeddable with each other with F at the bottom. And that's it. Thank you. Thank you very much.
All right, thank you. Let us thank Matt for a very interesting talk. Thank you. All right, so now if there are any questions to the speaker, you're welcome to ask them. So I had actually a couple of questions. This conjecture from your previous slide about, so could you show it again? So H here is not required to be finally generated. It's just any subgroup. I mean, I'm trying to understand the level of generality of this conjecture of what you're saying here.
I'm trying to think if it makes much of a difference. At the moment, I can't believe it makes much of a difference. So let's just say any subgroup.
Any subgroup, I see. Wait a second.
It's remarkably easy to contain a copy of F. It is extremely restrictive to have a subgroup of PL plus I that does not contain a copy of F. If your subgroup has two slopes that are not rationally related, it will contain a copy of F, and so forth and so forth and so on.
The other question I had was about F and the subgroups that appear in your construction, these G alphas, about the self-embeddability properties. So I'm trying to remember, I think F has a lot of self-embeddings, right?
Right.
And so what I don't remember now is, I mean, the images don't have to have finite index, right? You know, they can be sort of deep inside. That's also correct.
F has copies of F that are of finite index, and most of them have infinite index.
Right, that's what I thought, right? Okay. Okay, yeah, thank you. And it's probably the same or sort of almost the same. Well, I mean, with this.
These are fairly rigid.
Rigid,
I mean,
yes,
one of these groups is Z Wreath Z.
Right, yeah, so okay, so maybe it's not that,
you know,
but I don't remember now what the deal is with Z Wreath Z in terms of the images. I mean, it's
well, you know, I mean, Z Wreath Z, if you take the top group and you just restrict to the square of the generator, you have a copy of Z Wreath Z and Z Wreath Z.
Right, yeah.
So there will be a certain amount, but it's not as rife, if I can use the word rife mathematically, as it is with F. In an early paper, I said that F is riddled with copies of F. They're everywhere.
I see. Okay. Any other questions?
I have a question. I don't know, but can you hear me?
Yes. I can now.
Oh, okay. Thank you. Okay. So this is, I mean, F is such a singular group, and yet your arguments seem, to my sort of uninformed self, to be very general in a way. I mean, do you think that they apply in other situations?
We're working on a manifold of dimension 1. I'm very comfortable making statements about homeomorphisms there. If you want to try moving things around in other settings, I'm going to get a whole lot more hesitant. So the answer to your question is a very strong, I don't know. The construct doesn't really need to be in F. The construct needs to be in homeomorphisms of the interval or homeomorphisms of the line. And the fact that these things can be built so stably allows us to say, oh, by the way, they're actually all subgroups of F, which is almost an offhand remark. And since I'm interested in F and how weird it can be, the fact that these things are A, weird, and B, all subgroups of F pleases me. And as far as going outside of F, I don't know. I mean, PL plus I is something that I'm interested in as well. And manifolds of higher dimension, I'm pretty ignorant about. Sorry.
Oh, well, thank you. I mean, it was a kind of a uninformed question, but thank you for your answer.
Well, it was a very uninformed answer, so I think we match each other.
All right, very good. Any other questions? Okay, so let us thank Matt again. Thank you. I'll stop the recording now.